Okay, let's get into this. We're doing a deep dive today on what really feels like a breakthrough in vision language models. Our mission is to unpack SenseNova-MARS. That's a new multimodal agentic reasoning and search framework. We really want to understand how it's tackling these incredibly complex visual knowledge problems.
I think it's important to set the stage first.
Mhm.
Your traditional VLMs, the vision language models, they've always had this problem with dynamic integration.
Right.
They'd either get, bogged down in just text-based reasoning, or they'd call a tool then another tool, but all in isolation.
A very linear, rigid process.
Exactly. It's not human-like, and it really fell apart with high-resolution images, where the answer could be some tiny, tiny detail you'd miss.
Which is where SenseNova-MARS comes in, because it tackles that integration problem head on. They built this adaptive tool suite. So it's got image search, text search, and the really crucial one, this image crop tool.
And it's all managed through reinforcement learning. That coordination is the real leap here. To see what that really means, you have to look at how it handles a complex question. There's a case study they mention. The model gets asked about the age of a racing company, just from a logo on a driver's suit.
Okay, that's a tough one. How does it even start?
Well, first, it has to use the image crop tool. It zooms right in on that logo to figure out what it is. Let's say it identifies the company as Castor.
So it isolates the key visual information first.
Precisely. Then it triggers two totally separate text search queries on its own, one for the company's founding year and another for the racer's birth year.
Ah, so it knows it needs two different pieces of external knowledge.
Exactly. And only then does it do the final math to get the answer. It's this whole chain of perception, grounding, retrieval, and then calculation.
Right.
It's how a person would do it.
And it all hinged on first recognizing that tiny logo with the crop tool. That's where the magic is.
It is. And the performance numbers back it up. We're talking state-of-the-art among open-source models. On the standard search benchmark, MARS 8B hits a score of 67.84.
But does that kind of complex approach actually translate to a real-world advantage? Or is it just, optimized for one specific test?
It definitely translates. What's so interesting is that on several search-focused benchmarks, this 8 billion parameter model, MARS 8B, actually beats some of the big proprietary models like GPT-5 and Gemini 3 Flash.
Wow. Okay, so the architecture is validated then.
It is. And to really test it, the creators made a new benchmark. It's called Search.
So high resolution, I'm guessing.
Yep. It uses these massive 4K images where the tiny detail you're looking for might take up less than, say, 5% of the whole picture. It's designed to be brutal.
And how did it do?
It scored 41.64, which, on a test that hard, confirms it can do both that fine-grained visual work and connect it to the outside world.
So technically that brings up a question from it. You've got a continuous dual cropping mixed with discrete things like a search query. How do you stabilize the RL training for that? It seems like it would just collapse.
That was a huge hurdle. They actually had to introduce a new algorithm, a type of policy optimization, specifically to handle these diverse multi-tool paths. Essentially, it helps the agent figure out which tool deserves credit for a right answer when the tasks are so different. It's key to making the whole thing robust.
And you can see that paying off in how it behaves. The model shows this genuinely adaptive tool use.
It really does.
On standard tasks, it just uses search a lot. But throw one of those tough search images at it, and it immediately starts using the image crop tool way more. It pivots its strategy.
And it gets more efficient, too. The RL training cut down the average number of tools it needs from about 4 to just 2.
So the big picture here is that this framework pulls together external knowledge search and that really fine-grained visual analysis.
Yes. It's a huge step closer to how people solve these kinds of visual puzzles.
But the sources are also pretty clear about the limitations. Even with a perfect tool call, the model can get tripped up by what they call retrieval noise.
Right, like confusing based in with born in from a search result, or just not quite linking the thing it sees to the right search term.
Which leaves you with a really interesting final thought, doesn't it? We're getting really good at teaching the models how to use the tools. So is the next big bottleneck not about invoking the tool, but about teaching the model how to interpret and synthesize the messy, noisy, often contradictory information it gets back from the real world? Something to think about.